Hi everyone, this is the video lesson for 4.5, an algorithm for curve sketching, part 2. If you haven't watched the first part yet, please go back and watch it before continuing with part 2. Now in part 2, we're continuing with example number 1. Given the following functions, determine the domain, intercepts, asymptotes, critical points, intervals of increase and decrease, points of inflection, and concavity. Use this info or information to sketch the graph. Now, notice in the first case, this function is very straightforward. Y equals to x squared. Even with your grade 10 academic math background, you can tell y equal to x squared looks something like that. So in case you're thinking, why are we doing something so straightforward as example number 1a? The reason is to make sure that you form the habit of going through all these steps. So at this moment, we're going to pretend you do not know how to graph y equal to x squared. And we're going to use all these tools to get to that final step, which is graphing. So step 1, determine the domain. Domain equals to x is an element of real numbers. Number 2, intercepts. To find the intercepts, you can divide this into 2 different columns. In the first column, to find the x-intercept, you're going to set y to be 0. You're going to solve for x. And again, form the habit of finding the location and not just the x value. Likewise, when you find the y-intercept, you're going to set x to be 0, solve for y. And in this case, the xy intercepts are both located at 0, 0. So remember, graph as you go. This I mentioned back in part 1 of the video. To minimize your mistakes, graph as you go. Please don't graph at the very, very end. So 0, 0, just like that. Now, the next part is to find the critical points. So we know y equals to x squared. To find a critical point, you have to find the derivative, which is 2x in this case. You have to set this to be 0. You got to solve for x. And again, always form the habit of finding the critical point or points and not just the x value. Be mindful that most of the time, critical points are basically the maximum or the minimum. Sometimes the inflection point is embedded into the first derivative. So technically, to find the points of inflection, you have to set f double prime to be 0, but sometimes it's also inside the critical point. Now, intervals of increase and decrease. So again, you can compose a table, 2 different columns here, I, O, D, interval of increase and decrease. To find out the I, or the interval of increase, you set the derivative to be positive. And in this case, 2x is positive, for x must be positive. Likewise, to find the interval of decrease, you set the derivative to be negative. So x is going to be negative in this case. And again, we're going to come back to this. Your goal is to combine increase, decrease with concavity, and this table we're going to practice in the second last step before we put it together into a graph. So let's keep going. To find the points of inflection, let's go back up to the top. So we know y prime equals to 2x, which means when you find the derivative of y prime, which is y double prime, the derivative is going to be 2. Now, be mindful. In most cases, when you go through your homework, your test, your quiz, your final exam, it's extremely unlikely that the second derivative is going to be a constant. But it is because the example we're doing is too straightforward. So when it's x squared, y double prime, it's going to be 2. So again, to find the inflection point, you set this to be 0, and you discover that 0 cannot be 2. So there's no solutions to this. Or you can say there are no inflection points or no points of inflection. Now, just because you cannot find the point of inflection does not mean you cannot find the concavity. So again, this is a special case. The fact that y prime is going to be 2, this means it's always a positive number. This means for this function specifically, y equal to x squared, the function is going to be concave up for all values of x. Now, do not leave the second column blank. Make sure write down none to show that there's no x values that will make the function concave down. So here comes the most important table, and then we'll graph it, then we'll talk about the max and min. Again, this table we did, I'm just going to do it again with you. I want to make sure that you really, really, really know this. So again, press pause, try this. When you press play again, I'm going to continue. Okay, let's take a look. If the function is increasing and it's concave up, it's going to look like that. If the function is decreasing and it's concave up, it's going to look like that. In the third case, if the function is increasing and it's concave down, it's going to look like that. Last but not least, if the function is decreasing and it's concave down, it's going to look like that. So if I go back and I combine all of this, here's the number line. Now the divider is still going to be the critical point, 0, 0. And from here, we know the function will increase when it's positive. We also know the function is decreasing when it's negative. From here, we know the concavity, and it's always going to be concave up. So now, all you do is you go back and you say, well, how do I graph this? If it's concave up and decreasing, it's going to look something like that. What about the second case? Concave up and increasing, it's going to look something like that. Now, you put it all together, which looks roughly something like that. But again, you know more than just that idea. Since you did grade 10, you look at the step pattern, plug it back in, just like that. Now, what they didn't ask is the maximum and the minimum. So I want to go back a little bit and talk about it. So you can use the first and or the second derivative test to confirm. And I'm going to show you both. So the fact that the function is decreasing and it's increasing, that implies that the minimum is located at 0, 0. So that's called the first derivative test in the 4 cases. In the second derivative test, if you go back to the top, the fact that y double prime is always going to be positive, this means the function is always concave up, which means the minimum is going to be located at 0, 0. So there you have it. Example 1a, y equal to x squared. Example 1b, f of x equals to negative 3x cubed minus 2x squared plus 5x. And again, this is example 1 on page 208 from your textbook. Before I continue, try this. Go through the steps. Graph as you go. And in the next part, part 3, I will continue with example 1b. I hope this makes sense.